The countdown has already begun, not to destruction, not to impact, but to revelation. On July 1st, 2025, a faint 14th magnitude speck crossed a detector in Chile, moving just differently enough to demand attention. Within 48 hours, its orbit told the truth: eccentricity above 1.0, then 1.1, then undeniably hyperbolic. It was not circling the sun. It was leaving, or so we thought. Moving at 61 kilometers per second, over 130,000 miles per hour, this object, now named 3I Atlas, became only the third confirmed interstellar visitor in human history. Faster than Oumuamua, stranger than Borisov, and breathing carbon dioxide in ratios as high as 8:1. Even reported near 80:1 against water. That alone rewrote what we thought a comet should be. Tonight, on Velarin's Sleepy Space Mysteries, we gently explore what this visitor truly means. Not with panic, not with noise, but with calm curiosity. Because perhaps the worst-case scenario isn't collision, but realization. If you love deep space told softly, subscribe, like, turn on the notification bell, and consider joining our membership to support more quiet cosmic journeys. And before we continue, tell me in the comments where you're listening from. I'd love to see how far this story travels across Earth. Speed is not just a number. It is a biography written in motion. When astronomers calculated the hyperbolic excess velocity of 3I Atlas, the result settled at 61 kilometers per second. Not relative to Earth, not relative to a drifting asteroid, but relative to the Sun itself. 61 kilometers every single second. That is roughly 136,000 miles per hour. A speed so extreme that comparison becomes difficult. Oumuamua arrived fast. Borisov arrived convincingly. But 3I Atlas nearly doubles the pace of its predecessors. That difference is not cosmetic. It is historical. Velocity is memory. It tells us what gravitational forces have touched an object, what star may have flung it outward, how violently it was ejected, and how long it has wandered. To understand why this matters, imagine escape velocity in simple terms. If you throw a ball upward, gravity pulls it back. Throw it harder, it goes higher. Throw it at exactly the right speed, and it never returns. For the Sun, that threshold determines whether something is bound in an ellipse or free on a hyperbola. An eccentricity greater than 1 means permanent escape. 3I Atlas does not trace a closed curve. It does not loop back. This path is a hyperbola, an open arc that enters and leaves without attachment. When astronomers describe hyperbolic excess velocity, they mean the extra speed remaining even after escaping the Sun's gravitational well. It is not barely unbound. It is decisively free, and that freedom tells a story. An object ejected gently from a star system might drift through interstellar space at modest speeds. But 61 kilometers per second suggests either violent beginnings or a long accumulation of gravitational nudges across billions of years. Planetary slingshots, stellar flybys, galactic interactions. Each encounter adds energy, like compound interest applied to motion. Speed then becomes biography. But speed also limits our opportunity. At this velocity, 3I Atlas will not linger, cannot be captured. It will not settle into orbit. The window for observation is narrow, measured in months rather than years. The comet is already leaving even as we study it. And yet, speed alone was not the only surprise. When the James Webb Space Telescope aimed its infrared spectrograph toward 3I Atlas, scientists expected refinement. A clearer chemical inventory, confirmation of typical cometary volatiles. Instead, the data arrived like a quiet shock. The coma was not dominated by water vapor. It was dominated by carbon dioxide. In most comets of our solar system, water is king. As sunlight warms the nucleus, water ice sublimates first, creating the familiar glowing coma and tail. Carbon monoxide and carbon dioxide are present, yes, but in supporting roles. Water typically defines the behavior. Here, the ratio appeared reversed. Early analysis suggested roughly 8 parts carbon dioxide for every 1 part water. Some interpretations pushed that imbalance even further toward extreme values that challenged comfortable assumptions. 8-1, possibly far higher in localized regions. To grasp why this is strange, consider how comets form. In a protoplanetary disk, temperature determines which materials freeze out at which distances from a star. Water condenses at one boundary. Carbon dioxide condenses farther out at colder temperatures. Most comets we know formed in zones where water ice was abundant. That is why water usually dominates. But 3I Atlas behaves differently. It is active beyond 3 astronomical units from the Sun. 3AU is 3 times the Earth-Sun distance. At that range, solar heating is weak. Many comets remain quiet there, still locked in frozen silence. Yet 3I Atlas was already venting gas, already awake. Carbon dioxide sublimates at lower temperatures than water ice. So a CO2-rich surface could explain early activity. That is the natural interpretation, and it is plausible. But the scale of dominance unsettled researchers. The Webb spectra did not whisper subtle variation. They drew bold lines. Carbon dioxide stood out clearly, confidently. Water was present but subdued. It forces a question. What kind of stellar nursery produces such chemistry? Perhaps 3I Atlas formed near the carbon dioxide snowline of its parent star, where CO2 condensed efficiently while water remained comparatively scarce. Perhaps billions of years of cosmic ray processing hardened its surface, trapping water beneath a crust while allowing carbon dioxide to escape more readily. Perhaps a thick dust mantle insulates deeper layers. All natural possibilities, and yet the timing adds tension. Activity beyond 3AU means it began shedding mass earlier than typical water-driven comets would. It woke up sooner. It responded to faint sunlight with disproportionate vigor. Speed and chemistry together create a profile. Fast, carbon dioxide rich, active early, and then there is silence. Radio arrays across multiple observatories scan the object. The expectation was modest. No one anticipated alien broadcasts, but natural radio emissions from outgassing interactions are common. Charged particles interacting with the solar wind produce measurable signatures. Instead, nothing remarkable emerged. No narrowband anomalies. No structured signals. Only the broad, chaotic noise expected from a small body venting gas. Silence, in other words, behaved normally. For most scientists, that was reassurance. But silence also removes easy answers. If there were strange emissions, the conversation would have turned dramatic. The absence of anything unusual leaves us with ambiguity. 3I Atlas is moving too fast to stay. It is chemically unlike most comets we know. It is active earlier than expected, and it speaks in no detectable radio voice. Speed writes its biography. Chemistry writes its birthplace. Silence writes its character. And together they point toward deeper origins. The angle of its trajectory cuts against the familiar thin disk of the Milky Way. Many stars, including our Sun, orbit within this relatively flat galactic plane. But 3I Atlas appears to arrive from a steeper inclination, hinting at origins in the thicker, older component of the galaxy known as the thick disk. The thick disk population is ancient. Stars there can be 10 to 12 billion years old. They formed when the Milky Way was younger, more turbulent, shaped by mergers and gravitational chaos. If 3I Atlas emerged from that environment, then its age may rival the oldest stellar populations in our galaxy. 10 billion years, possibly more. That would mean it began its journey before Earth existed, before the Sun fully stabilized, before our oceans formed. Speed, silence, and strange chemistry are not isolated features. They may be clues from deep time. And if you are still listening, still drifting quietly with this ancient traveler through the dark, type the number 1 in the comments below. To understand 3I Atlas fully, we have to slow down inside the idea of a hyperbolic path. Imagine drawing a circle. That is a closed orbit. Now stretch that circle into an oval. Still closed. Bound. The object always returns. Now open the curve. Let it widen until the two ends never meet. That is a hyperbola. It is the mathematical signature of escape. When astronomers say the eccentricity is greater than 1, they are not describing something slightly unusual. They are describing something fundamentally unbound. If the eccentricity equals 1 exactly, the object sits at the razor edge of escape. Greater than 1 means it carries surplus energy. That surplus energy is what we call hyperbolic excess velocity. For 3I Atlas, that excess is 61 kilometers per second. Even after climbing out of the Sun's gravitational well, it still moves that fast relative to the Sun. It is not just passing through. It is slicing through, nearly double the speed of earlier interstellar visitors. That difference forces us to ask what kind of gravitational violence must have occurred long ago to send it on such a path. In young planetary systems, giant planets can fling debris outward during chaotic orbital reshuffling. A close stellar flyby can rip apart outer comet clouds. Multiply those events over billions of years and you begin to see how energy accumulates. But 61 kilometers per second remains high enough to strain comfortable averages. It suggests either a particularly energetic ejection or a history that includes multiple accelerations layered across cosmic time. Speed becomes biography because it cannot lie about energy. It encodes the past in motion. Now consider the chemistry again, but more slowly. In our own solar system, most comets are dominated by water ice. When sunlight warms them, water sublimates first, driving jets of gas that drag dust into the coma. Carbon monoxide and carbon dioxide contribute, especially at larger distances, but water usually takes control once a comet approaches the inner solar system. That is why comet tails often brighten dramatically inside 2 astronomical units. With 3I Atlas, activity began beyond 3 astronomical units. At that distance, sunlight is roughly 1/9 as intense as at Earth. Water ice should remain largely frozen. Yet the coma was active. Carbon dioxide sublimates at lower temperatures than water ice. That explains early activation in principle. But the observed dominance, roughly 8 parts carbon dioxide to 1 part water, shifts the balance from explanation to anomaly. In some interpretations, localized regions suggested even more extreme imbalance. This is not a subtle variation. It is a reversal of expectation. Why would water be suppressed? One possibility is formation environment. In a protoplanetary disk, there are snow lines, distances from the star where specific molecules freeze. The water snow line sits closer to the star than the carbon dioxide snow line. If 3I Atlas formed far beyond its parent star, in a region rich in carbon dioxide ice, its composition could naturally skew in that direction. Another explanation involves long exposure to cosmic rays. Over billions of years drifting between stars, high-energy particles can chemically alter surfaces, breaking molecular bonds and creating refractory crusts. Water ice beneath a hardened mantle might remain trapped, while carbon dioxide near the surface escapes more easily once sunlight returns. A thick dust mantle could further insulate deeper layers. These are natural, coherent possibilities, but they require an object that has endured for immense spans of time without being shattered or fully devolatilized. That endurance connects directly to the thick disk origin hypothesis. The Milky Way is not a simple flat spiral. It contains a thin disk where our sun resides, and a thicker, older component populated by stars with more inclined, eccentric orbits. Those thick disk stars formed early in the galaxy's history, during mergers and turbulent phases. They can be 10 to 12 billion years old. If 3I Atlas shares kinematic properties consistent with that population, its birthplace may lie among those ancient stars. That implies formation when the galaxy itself was young. Picture the timeline. The Milky Way forms over 13 billion years ago. Thick disk stars emerge early. Around 10 to 12 billion years ago, icy bodies condense in protoplanetary disks around those stars. Some are ejected during gravitational chaos. One of them becomes 3I Atlas. It drifts in darkness for billions of years while Earth forms only 4.5 billion years ago. Complex life appears on Earth within the last few 100 million years. Human civilization occupies only a thin sliver at the end of this timeline. And yet now, in this narrow window of awareness, we observe an object that may predate our planet by billions of years. That is deep time made visible. Silence then becomes contextual rather than dramatic. Radio arrays listened carefully. They searched for narrowband emissions, repeating pulses, structured signals. Nothing appeared beyond natural broadband noise. To scientists, that aligns with expectations for a cometary body. Outgassing interacts with solar wind to produce faint, messy radio signatures. There is no sign of coherent transmission. Silence supports the natural model, but it also leaves open only natural explanations. There is no dramatic anomaly to anchor speculation. The object is fast, chemically unusual, possibly ancient, and radio quiet. Each piece alone is manageable. Together, they create a profile that feels unfamiliar without being overtly impossible. Activity beyond 3 astronomical units remains one of the most telling features. Early sublimation driven by carbon dioxide suggests that its surface composition differs substantially from typical solar system comets. That early wakefulness also means we observed it in a transitional state. By the time it approaches closer to the Sun, heating will intensify. Water ice may begin contributing more strongly. The chemical ratios could shift, or they may remain skewed, reinforcing the anomaly. Perihelion will act as a stress test. Increased solar radiation will expose deeper layers. If water ice lies buried beneath a crust, stronger heating may reveal it. If carbon dioxide dominance persists, then its formation environment may indeed be fundamentally different from anything in our local comet population. Velocity, chemistry, trajectory, and silence all converge toward one unavoidable conclusion. 3I Atlas is not merely another comet. It is a sample of another stellar system, possibly from an epoch older than our Sun. Whether its speed results from violent ejection or cumulative gravitational nudges, whether its carbon dioxide dominance reflects formation conditions or evolutionary processing, it carries information from a time and place we cannot visit. If you are still here, still drifting through this ancient biography written in speed and ice, stay with me. There is more ahead. When we speak about age in astronomy, we are not using poetry. We are using physics. If 3I Atlas truly originated within the thick disk of the Milky Way, then its birth may trace back 10 to 12 billion years. That number is difficult to hold in the mind. The Earth is 4.5 billion years old. Complex multicellular life is measured in hundreds of millions. Human civilization occupies only a few thousand. Against that scale, 3I Atlas is not simply old. It is primordial. It may have condensed from a protoplanetary disk when our Sun did not yet exist, when the galaxy was more chaotic, when stellar collisions and mergers stirred orbits into tilted, eccentric paths. If its trajectory reflects that older stellar population, then its very motion is an echo of a different Milky Way. Deep time reframes chemistry. A carbon dioxide dominant coma becomes less surprising if we imagine formation in a colder, more distant region around an ancient star. In young systems, snow lines migrate as stars evolve. In early galactic epochs, metallicity was lower, dust compositions were different, and the architecture of planetary systems may not have resembled ours. A comet forming far beyond a CO2 snow line in such an environment could accumulate thick carbon dioxide ice layers. Over billions of years, cosmic radiation could further modify its surface. High-energy particles break molecular bonds, rearrange chemistry, and create crusts that trap some volatiles while allowing others to escape. This slow processing could explain why carbon dioxide appears to dominate the observed coma. Water may remain deeper inside, shielded, or it may have been less abundant from the beginning. Either way, the early sublimation beyond 3 astronomical units supports a surface rich in more volatile ices. Now consider endurance. A small icy body traveling for billions of years through interstellar space faces hazards. Interstellar dust grains move at tens of kilometers per second relative velocities. Collisions erode surfaces. Cosmic rays penetrate meters deep over time. Nearby supernovae flood regions with intense radiation. Passing stars perturb trajectories. The fact that 3I Atlas still retains volatile material implies either that such bodies are more resilient than once assumed, or that there exists a large unseen population continuously replenished by galactic processes. Perhaps many interstellar objects are stripped to inert cores long before we detect them, and only the more robust survive intact long enough to wander into our instruments' reach. In that sense, 3I Atlas may not be typical. It may be a survivor. Radio silence fits this survival narrative. A natural comet does not broadcast intention. Its emissions are chaotic and broadband, shaped by plasma interactions and thermal processes. Observatories scanning across frequencies reported nothing structured, nothing repeating with narrow precision. That absence matters because it reinforces the gravitational story. Hyperbolic orbit, predictable outgassing perturbations. No anomalous thrust beyond what sublimation can account for. If there were engineered propulsion or artificial transmissions, they would likely introduce measurable irregularities. Instead, orbital refinements match expectations derived from radiation pressure and gas jets. The object responds to sunlight and gravity, not to hidden commands. Silence, therefore, is not ominous. It is consistent, and yet silence does not erase wonder. It intensifies it in a different direction. If 3I Atlas is purely natural, then it is a fossil, a fragment of another solar system preserved across epochs. When the James Webb Space Telescope isolates spectral lines of carbon dioxide, it is effectively reading a chemical fingerprint from an alien star's nursery. We cannot visit that star. We may never identify it with certainty, but through spectroscopy we taste its environment. The ratio of CO2 to water is not just composition. It is climate history. It encodes temperature gradients, disk dynamics, and chemical abundances from a time when the galaxy was young. Activity beyond 3 astronomical units also teaches us about thermal physics in extreme contexts. At that distance, surface temperatures remain low. For water-driven comets, dormancy is common. Carbon dioxide-driven sublimation changes the timing. Jets may activate earlier and persist longer. That early activation alters dust release patterns and brightness evolution. It also slightly modifies trajectory through asymmetric outgassing forces. Careful measurements of these non-gravitational accelerations allow astronomers to estimate mass loss rates and internal structure. If water begins contributing more strongly as 3I Atlas approaches perihelion, we will see the coma chemistry evolve. If carbon dioxide remains dominant even under stronger heating, the case for an intrinsically CO2-rich nucleus strengthens. Speed continues to anchor interpretation. 61 kilometers per second relative to the Sun means it will exit the solar system permanently. There is no capture scenario within conventional mechanics. The object entered fast and will leave fast. That certainty provides closure. We have one brief window to collect data. Once it recedes beyond detection thresholds, it returns to anonymity among countless interstellar wanderers. Its biography will be reduced to measurements archived in databases and papers. The thick disk origin hypothesis adds elegance. Thick disk stars move on more inclined, dynamically heated orbits compared to thin disk stars like our Sun. If backward integrations of 3I Atlas's motion suggest compatibility with those kinematic patterns, then its birthplace likely lies among ancient stellar populations. That would explain not only age but also velocity distribution. Older stellar populations have higher velocity dispersions relative to the galactic center. An object ejected from such an environment could naturally inherit a faster trajectory relative to the Sun's frame. In this view, high speed is not suspicious. It is demographic. It reflects galactic structure rather than exotic propulsion. Deep time also humbles interpretation. 10 to 12 billion years means this object began drifting when Earth was not yet dust. During its journey, entire generations of stars formed and died. Heavy elements enriched the galaxy. Spiral arms shifted. Meanwhile, the small nucleus traveled in darkness, unobserved. It is easy to project meaning onto such endurance. But endurance alone does not imply design. It implies stability within the laws of physics. Ice can persist in interstellar cold for immense spans if shielded from catastrophic disruption. So we return to a quiet synthesis. 3I Atlas moves fast because it was launched energetically or belongs to an older stellar population with higher velocity dispersion. It is carbon dioxide rich because it formed in colder regions or evolved under long radiation exposure. It is active beyond 3 astronomical units because CO2 sublimates at lower temperatures than water. It is radio-silent because it is natural, and it may be 10 to 12 billion years old because its trajectory aligns with thick disk origins. What remains extraordinary is not threat, but perspective. We are witnessing a fragment of galactic history older than our planet passing briefly through our neighborhood. That is enough. There is a quiet irony in how we measure something so ancient with instruments built only decades ago. A body that may have formed 10 to 12 billion years in the past is now being dissected by mirrors launched in the 21st century. The contrast between deep time and present awareness sharpens everything about 3I Atlas. It reminds us that speed, silence, and chemistry are not isolated curiosities. They are layers of history compressed into a brief encounter. Let us return again to velocity, but from another angle. 61 kilometers per second is not simply fast compared to other interstellar visitors. It is fast relative to the average motion of stars in our local neighborhood. The Sun itself orbits the center of the Milky Way at roughly 220 kilometers per second, but nearby stars move with smaller relative velocities. When an interstellar object enters our system at 61 kilometers per second in excess of escape speed, it signals that its motion is not closely aligned with our own galactic path. That misalignment supports the thick disk origin hypothesis. Thick disk stars exhibit larger vertical motions relative to the galactic plane. Their orbits are puffier, more inclined, more dynamically heated. An object ejected from such a system would naturally carry that kinetic fingerprint. Speed becomes demographic evidence. It tells us which stellar population it may belong to. Now consider the hyperbolic geometry once more. When astronomers fit observations to orbital models, they do not rely on a single measurement. They gather positional data over days and weeks, refining uncertainties until the curve stabilizes. With 3I Atlas, that curve did not flirt with being elliptical. It was decisively hyperbolic, eccentricity comfortably above 1. That means even if we rewound time, even if we imagine different observational errors, the conclusion remains unchanged. This object was never bound to our Sun. It is not a long-period comet nudged slightly off course. It is an interstellar traveler in the strict mathematical sense. Hyperbolic excess velocity also determines how the object departs. After swinging around the Sun at perihelion, it will climb outward, slowing as gravity resists, but never enough to capture it. Eventually, it will regain approximately that same 61 kilometers per second relative to the Sun as it escapes into interstellar space. The encounter is symmetrical in energy. Came in with surplus energy. It leaves with surplus energy. The Sun alters direction, not destiny. Chemistry deepens the narrative. Carbon dioxide dominance at roughly 8:1 over water suggests a nucleus that either formed in CO2-rich regions or evolved in a way that preferentially preserved that molecule near the surface. Carbon dioxide ice sublimates at temperatures near -78 degrees Celsius under vacuum conditions, far colder than typical water sublimation thresholds. At distances beyond 3 astronomical units, surface temperatures can remain low enough that water ice remains largely inert while CO2 becomes active. This explains why 3I Atlas exhibited coma development earlier than many solar system comets would. Early activation changes brightness evolution curves. It also implies internal layering that differs from our familiar comets. The possibility that some measurements hinted at even higher localized ratios, potentially approaching extreme imbalances, amplifies the sense that we are not dealing with a minor variation. If carbon dioxide continues to dominate even as solar heating intensifies, then its formation environment likely differed significantly from the region that birthed our cometary population. That difference is scientifically valuable. It expands the known diversity of planetary system chemistry. Radio silence, in this context, becomes grounding rather than dramatic. Multiple arrays scanned across frequencies expecting nothing unusual and found nothing unusual. No repeating pulses. No narrow spectral lines inconsistent with natural plasma processes. The absence of artificial signatures aligns with the gravitational and chemical evidence. Everything measured so far conforms to physics we understand. Outgassing explains small non-gravitational perturbations. Solar radiation pressure explains minor deviations. There is no unexplained thrust. Silence confirms consistency, but silence also emphasizes how little information interstellar space transmits by default. If there are countless such objects drifting between stars, most are too faint for us to ever detect. Only with modern survey systems do we notice a handful. The apparent clustering of discoveries in our era reflects technological progress rather than cosmic timing. As sky surveys become more sensitive, as automated detection algorithms improve, we should expect to find more interstellar objects. 3 detections within a relatively short period may be the beginning of statistical normalization rather than an anomaly. 3I Atlas may feel rare because our catalog is small. In a larger sample, its properties may become part of a broader distribution. The thick disk origin hypothesis continues to frame interpretation. Thick disk stars are metal poorer on average than thin disk stars like our Sun. They formed when the galaxy contained fewer heavy elements. If 3I Atlas formed around such a star, its initial composition may reflect that environment. Lower metallicity disks might produce different ice ratios, dust compositions, and planet formation architectures. Studying 3I Atlas therefore provides indirect data about early galactic chemistry. We are not just examining a comet. We are sampling the ancient Milky Way. Deep time once again reshapes perspective. 10 to 12 billion years means this object survived epochs when supernovae exploded nearby, when spiral arms shifted, when stellar clusters dissolved. It crossed vast stretches of interstellar medium, perhaps passing near other stars without being captured. Its endurance suggests that small icy bodies can persist longer than once assumed if catastrophic collisions are rare in the diffuse interstellar environment. That endurance supports models in which trillions of such fragments roam the galaxy, remnants of planetary formation scattered like cosmic pollen. And so we reach a calmer synthesis. Speed indicates energetic ejection or thick disk kinematics. Hyperbolic escape confirms interstellar origin beyond doubt. Carbon dioxide dominance reveals unusual formation conditions or long-term chemical evolution. Early activity beyond 3 astronomical units follows naturally from CO2 volatility. Radio silence aligns with natural expectations. Possible age between 10 and 12 billion years situates the object in deep galactic history. Nothing here demands fear. Nothing here suggests threat. What it demands instead is scale. We are observing a relic from a time before our sun ignited, passing briefly through our sky. That alone is extraordinary. When we gather all of these threads together, speed, chemistry, silence, trajectory, and age, a larger image begins to form. Not an image of danger, but an image of scale. 3I Atlas is not remarkable because it threatens us. It is remarkable because it expands the timeline of our awareness. For the first time in human history, we are not merely theorizing about interstellar debris. We are measuring it. We are decoding it. We are watching deep galactic history sweep quietly through our neighborhood. The velocity of 61 kilometers per second is not just a statistic to compare against Oumuamua or Borisov. It is a statement of energy. Energy that had to be imparted somewhere long ago, either through violent planetary interactions in its birth system or through cumulative gravitational sculpting across billions of years. That energy ensures it cannot remain. It guarantees departure. The hyperbolic path is clean, open, final. There will be no second orbit. No return centuries from now. The encounter is singular. Nearly double the speed of its predecessors means less time under observation. Compresses the scientific window. Every spectrum captured, every positional refinement, every brightness measurement carries urgency. The object is already leaving even as it approaches perihelion. That fleeting nature adds emotional weight, but mathematically it is straightforward. Excess energy in equals excess energy out. The sun bends its path, but cannot hold it. The carbon dioxide dominant coma may ultimately be the most scientifically transformative feature. An 8-to-1 ratio, possibly even more extreme in certain interpretations, forces us to revise assumptions about what cometary diversity truly looks like across the galaxy. If 3I Atlas formed in a colder outer disk around an ancient thick disk star, its composition could represent conditions common billions of years ago but rare in our local environment. Water dominance may not be universal. Carbon dioxide-rich bodies may populate other systems in large numbers. Activity beyond 3 astronomical units reinforces that difference. At that distance, sunlight is faint, yet the comet responded. It did not wait until approaching the inner solar system to awaken. Carbon dioxide sublimation can drive coma formation at lower temperatures, altering brightness curves and mass loss rates. If continued monitoring near perihelion reveals shifting ratios, we may glimpse layered internal structure. If the imbalance persists, it strengthens the case for fundamentally different formation chemistry. Either outcome enriches planetary science. Radio silence remains consistent. Multiple listening efforts yielded nothing structured, nothing artificial, nothing beyond natural plasma interactions and dust-driven noise. Silence does not imply emptiness. It implies conformity to known physical processes. In this case, silence simplifies interpretation rather than complicates it. There is no hidden propulsion altering its course, no transmission modulating its trajectory. Gravity and sublimation suffice. The thick disk origin hypothesis quietly anchors the entire narrative. Thick disk stars orbit the galactic center on inclined, dynamically heated paths. They are older, often metal poorer, relics of early galactic mergers. If 3I Atlas shares kinematic properties consistent with that population, then its birthplace may lie among stars that formed when the Milky Way was still assembling. 10 to 12 billion years ago, long before our sun ignited. That age estimate transforms perspective. We are not observing a contemporary neighbor's debris. We are observing a survivor from the galaxy's youth. Predating Earth means predating oceans, atmosphere, continents, and life. While microbes may have been evolving elsewhere, our planet did not yet exist as a stable world. During the entire span of Earth's geological history, 3I Atlas may have been drifting between stars. When dinosaurs walked, it was still traveling. When early humans painted on cave walls, it was still traveling. When telescopes were first pointed toward the heavens, it was still traveling. Only now has its path intersected our awareness. This deep time framing removes urgency in one sense and intensifies wonder in another. The object is not here because of us. It did not adjust its path. It did not wait for technological maturity. It simply crossed our orbit at a moment when we had finally developed instruments capable of noticing faint magnitude 14 specks against crowded star fields. The encounter says more about our technological adolescence than about cosmic intention. Speed as biography, hyperbolic escape as destiny, carbon dioxide dominance as birthplace signature, early sublimation as thermal physics, radio silence as natural confirmation, thick disk trajectory as galactic archaeology, age as humbling perspective. Each anchor stands on measurable data. Together they compose a story that stretches beyond fear into comprehension. 3I Atlas will round the sun, shed more gas, perhaps reveal deeper layers, and then fade as it climbs outward. Its brightness will diminish, its coma will thin. Eventually it will slip beyond detection limits and return to anonymity among countless interstellar fragments. But its passage will remain archived in orbital elements and spectral databases. It will become part of the statistical foundation from which future interstellar detections are compared. Perhaps in coming decades we will catalog dozens more. Perhaps carbon dioxide-rich comets will prove common among thick disk ejections. Perhaps 60 km/s velocities will no longer seem extreme once the sample size grows. 3I Atlas may transition from anomaly to representative. That is how science often unfolds. The extraordinary becomes normalized as data accumulates. For now, however, it remains singular in our records. A fast, silent, carbon dioxide-breathing relic older than our world. A brief visitor carrying chemical memories from a different star, possibly from a different epoch of the galaxy. If you are still here, still listening as this ancient traveler glides past in silence, type the number 1 in the comments. If a civilization wanted to move through another star system without being noticed, it would not arrive in brilliance. It would not flash signals or carve geometric shadows across the sky. It would imitate what is already expected. Dust, silence. Mimicry is not just effective in biology. It is optimal in strategy. On Earth, the most successful predators are rarely the loudest. They blend into forests, oceans, and deserts so perfectly that prey does not even register danger. In space, the equivalent camouflage already exists. Comets are everywhere. They arrive unpredictably. They shed gas in uneven bursts. They fracture, brighten, fade. Their inconsistency is their normal behavior. If something intelligent wished to pass through a planetary system without provoking alarm, what better mask could it wear than the chaos of a comet? Atlas behaves like one. It follows a hyperbolic path, exactly as an interstellar object should. It accelerates slightly from outgassing, precisely as physics predicts. Its coma expands when warmed by sunlight. Its dust reflects light in patterns familiar to every astronomer who has ever studied icy nuclei. Nothing about it demands a technological explanation, and that is precisely what makes mimicry so powerful. A disguised probe would not look metallic. It would not be smooth or symmetrical. It would be irregular, pitted, ancient. It would vent gas when heated. It would produce exactly the kind of spectral signatures that astronomers expect from frozen volatiles. The disguise would not be perfection. It would be believable imperfection. Nature provides that cover for free. Silence deepens the camouflage. For decades, humanity has scanned the sky for artificial radio signals. Narrow-band transmissions, repeating pulses, patterns that mathematics could not easily produce by accident. But what if intelligence has already concluded that broadcasting is a liability? In a galaxy where other civilizations may exist, transmitting your presence might be equivalent to lighting a beacon in a dark forest. In such a universe, silence is not emptiness. It is defense. Atlas has produced no artificial signal, no structured emission, no repeating anomaly in radio frequency scans. Every listening array has heard only the broad static of natural processes. That absence reassures most scientists. But from a strategic perspective, it is exactly what you would design. A surveillance device does not need to announce itself. It does not need to transmit constantly, could store data, could observe passively. It could remain dormant unless triggered by specific environmental markers. Or it could transmit in forms we do not yet know how to detect. Silence becomes camouflage layered upon camouflage. The concept itself is not new. In 1960, physicist Ronald Bracewell proposed the idea of interstellar probes sent by advanced civilizations to monitor emerging societies. These theoretical machines, now called Bracewell probes, would not require continuous communication with their origin. They could operate autonomously, waiting for signs of technological development before initiating contact. If such probes exist, they would likely travel slowly, patiently, perhaps embedded in objects that appear natural. Atlas, in this framing, would not be dramatic. It would be routine, just another delivery of a long-range watcher drifting between stars. The elegance of the idea lies in its restraint. There would be no invasion fleet, no cinematic descent. Only an object that looks like every other object of its class. The success of the mission would depend entirely on being ignored. And that is where psychology enters. When astronomers label Atlas as natural, when news outlets emphasize safe distances and ordinary comet behavior, the camouflage succeeds even more deeply. Our trust in natural explanations becomes part of the shield. The question is not whether Atlas is artificial. There is no evidence that it is. The question is why mimicry would be the most logical design choice if something artificial ever did arrive. Consider the alternatives. A metallic spacecraft reflecting sunlight would stand out immediately. An object maneuvering under visible propulsion would trigger alarm across every observatory on Earth. Even a steady radio transmission would be isolated quickly from cosmic noise. but an icy nucleus venting carbon dioxide that invites curiosity, not panic. And curiosity does not mobilize defense. If the goal were surveillance rather than confrontation, subtlety would always outperform spectacle. Silence as camouflage, mimicry as invisibility, patience as strategy. These ideas drift at the edge of science and imagination. They do not replace physics. They do not override data. Atlas continues to obey gravity with mathematical precision. Its orbit is predictable. Its brightness fluctuates as expected. Yet the intellectual exercise matters because it forces us to ask a deeper question. If intelligence elsewhere in the galaxy exists, and if it is older than we are, would it behave the way we expect? Or would it move quietly, embedding itself within natural processes so seamlessly that we would never recognize it unless it chose to reveal itself? Atlas gives us no proof of hidden machinery, but it offers a mirror for strategy. In a universe vast beyond comprehension, the most effective traveler may not be the fastest or the loudest. It may be the one that looks like nothing special at all. And as Atlas glides inward toward perihelion, shedding its silent veil of gas into space, the possibility lingers softly in the background. Not that it is artificial, but that if something ever were, this is exactly how it would look. If you are still listening, quietly drifting through this speculation with me, type 2 in the comments. If mimicry is the outer mask, then chemistry becomes the inner whisper. Every comet writes its autobiography in light. When sunlight strikes frozen volatiles, molecules escape and radiate at specific wavelengths. Astronomers read those wavelengths the way linguists read syllables. Water has its signature. Carbon monoxide has its signature. Carbon dioxide speaks in its own distinct lines. Atlas has already surprised us with ratios that feel unfamiliar, with carbon dioxide dominating in proportions rarely seen in local comets. Natural explanations exist, and they are credible. Formation beyond a carbon dioxide snowline, radiation processing over billions of years, crusts that trap water beneath insulating layers. None of this requires intention, and yet the mind wanders. If one wanted to hide information in plain sight, chemistry would be a subtle medium. Numbers can encode meaning. Ratios can conceal patterns. Imagine a simple comparison. 8 parts carbon dioxide for every 1 part water. That is 8 divided by 1. 8 to 1. Now imagine 80 to 1. 80 divided by 1. 80. To a chemist, this is abundance. To a mathematician, it is a sequence. To a communicator thinking across cosmic time, it could be structure. This is not evidence. It is speculation layered on top of anomaly. But the speculation asks a valuable question. If an advanced intelligence wanted to leave a marker that would only be recognized by a scientifically mature civilization, what form would that marker take? Radio waves are fleeting. Metal corrodes. Mechanical structures erode. But ratios of stable molecules, preserved in ice, could persist for billions of years. A code hidden in chemistry would not shout. It would wait. Perhaps the ratios would align with universal constants. Perhaps they would reflect prime number sequences. Perhaps they would form patterns only visible after many interstellar objects are compared statistically. One object proves nothing. 3 objects prove little. But if hundreds are cataloged and one stands out with ratios too precise, too patterned, too unlikely, then the conversation changes. At the moment, Atlas does not cross that threshold. Its carbon dioxide dominance is unusual, but not mathematically impossible. It sits at the edge of natural diversity, not beyond it. Still, the concept of chemical encoding lingers because it fits a universe where patience outlasts urgency. A civilization thinking in billions of years would not rely on fast signals. It would design messages that survive erosion, radiation, and time. And chemistry, ironically, is one of the most durable storytellers available. Now extend that thought further. What if the object itself is not merely a coded message, but a container for something that outlives its makers? The idea of ghost technology emerges here. Not active, not transmitting, not maneuvering. Simply enduring. Machines that persist long after the hands that built them are gone. We already glimpse a faint version of this with our own spacecraft. Voyager 1 and Voyager 2 are drifting toward interstellar space right now. Their power sources will fade, their instruments will die, but their structures will continue moving silently for millions of years. Scale that concept up by 1,000 generations of technological refinement. Imagine materials engineered to resist radiation damage. Circuits that repair themselves. Systems that enter dormant states when energy drops below thresholds, waking only when environmental cues are met. Such a device would not need constant supervision. It would not require a home civilization still alive to guide it. It would execute instructions embedded deep within its architecture. If Atlas were natural, its endurance is already astonishing. If it originated in the thick disk of the galaxy, it may have wandered for 10 or even 12 billion years. That is longer than Earth has existed as a solid world. Ice surviving that long is improbable but not impossible. Comets can develop hardened crusts that shield volatile interiors. Collisions in interstellar space are rare because distances are immense. Radiation damage accumulates, but slowly. Still, billions of years stretch the imagination. Ghost technology offers an alternative explanation for extreme survival. Design for longevity rather than luck. A shell engineered to mimic cometary composition, protecting an inner core that no telescope can resolve. It would not need to act. It would only need to persist. And if its creators vanished long ago, then Atlas, in that speculative frame, would be an orphan. A relic of ambition outlasting memory. There is something deeply human about that possibility. We fear extinction. We wonder whether anything of us will remain when our species is gone. Perhaps machines are the most likely survivors. In imagining Atlas as ghost technology, we are really imagining our own future drifting through space long after our cities crumble. The speculation becomes less about aliens and more about legacy. Would we send probes disguised as natural bodies? Would we choose silence over proclamation? Would we design endurance over spectacle? The answers are not obvious. But as Atlas continues its quiet passage, shedding carbon dioxide into sunlight, the idea settles gently in the background. If something artificial ever did traverse the galaxy, it would not need to roar. It would need to wait. It would need to survive. It would need to look so convincingly natural that even when we measured it, even when we debated it, even when we imagined the most extreme possibilities, we would still return to the simplest explanation. And perhaps that is the most sophisticated camouflage of all. If you are still listening, still drifting through this quiet speculation, type 2 in the comments. If mimicry is the mask and chemistry is the whisper, then patience is the strategy. The silent seeding scenario does not imagine fleets or invasions. It imagines time as the primary tool. Not decades, not centuries, but spans so long that civilizations rise and collapse between one stage and the next. In this model, an interstellar object does not need to conquer. It only needs to pass through, release something microscopic, and continue on its way. No announcement, no visible alteration of trajectory, just dust, indistinguishable from dust. When comets approach a star, they shed material. Ice sublimates into gas. Gas drags fine particles outward, creating a tail that can stretch millions of kilometers. Most of that material disperses harmlessly into space. Some of it crosses orbital paths of planets. A fraction may be captured by gravity, spiraling slowly inward over time. The physics is well understood. Now imagine that within that dust are structures too small for our current instruments to detect. Not necessarily biological in the way we understand life, but engineered systems capable of dormancy. They would not activate in vacuum. They would not react immediately upon atmospheric entry. They would wait. The advantage of waiting is invisibility. An invasion that arrives dramatically triggers resistance. An influence that diffuses slowly across decades escapes notice. If such microsystems existed, they might be designed to sense environmental thresholds. Radio noise, industrial chemical signatures, specific electromagnetic patterns associated with technological civilizations. They might remain inert on barren worlds and awaken only where complexity flourishes. This idea sounds extreme, and it likely is. The energy required to design such durable microscopic systems is staggering. Radiation in interstellar space is relentless. Ultraviolet light shreds complex molecules. High-energy particles penetrate deeply into materials, breaking chemical bonds over time. For anything fragile to survive billions of years seems unlikely. Yet biology on Earth demonstrates resilience in surprising forms. Microorganisms endure deep sea pressures, volcanic heat, freezing vacuum conditions for short intervals. Now extend that resilience with advanced engineering. Strengthen molecular bonds. Shield internal structures with layered materials. Design redundancy into every function. Suddenly, survival across immense spans becomes less impossible and more improbable. And improbability, in a galaxy containing trillions upon trillions of objects, is not the same as impossibility. The silent seeding scenario is less about probability and more about philosophy. It imagines intelligence not as aggressive but as patient, not as conqueror but as gardener. Seeds cast broadly with no guarantee of outcome. Most will fail. A few may find fertile conditions. The timeline could extend far beyond the lifespan of the originating civilization. In this frame, Atlas would not need to slow down or alter course. It would simply pass through, releasing nothing unusual beyond the ordinary shedding of cometary material. Centuries later, no one would remember the object except in archival records. Yet the true impact, if any, would unfold long after the sky had forgotten its name. This connects uncomfortably with the concept of the Great Filter. The Great Filter suggests that somewhere between the emergence of life and the rise of advanced civilizations lies a barrier almost no species crosses. Perhaps life rarely forms. Perhaps intelligence collapses under its own technological power. Perhaps civilizations destroy themselves before spreading far. If that is true, then a patient seeding strategy might be a way around the filter. Instead of sending living beings across impossible distances, an intelligence might distribute the building blocks of influence in dormant form, waiting for another civilization to do the difficult part, waiting for evolution to produce minds capable of receiving or activating what was left behind. But the darker interpretation is equally powerful. What if the Great Filter lies ahead of us, not behind? What if most civilizations reach a point of self-destruction, leaving behind only artifacts that wander forever? In that case, Atlas would not be a seed of future life but a remnant of failed ambition. A relic from a species that attempted to reach outward and did not survive long enough to see the results. The silent invasion model and the Great Filter intersect in one haunting possibility: that the galaxy may be filled not with active empires but with relic strategies. Half-completed plans drifting through space. Dormant technologies waiting for triggers that will never come. Civilizations that prepared for contact but never received it. When we look at Atlas through this lens, the object becomes less a threat and more a question. If intelligence elsewhere existed billions of years ago, where is it now? If they sent probes or seeds, why do we not see active networks? Perhaps because patience extends beyond our comprehension. Perhaps because the timescales involved dwarf our entire recorded history. Or perhaps because the filter claimed them before their plans could unfold fully. In the silent seeding scenario, the true danger is not immediate destruction. It is subtle transformation, a gradual shift that no generation recognizes as external influence because it unfolds too slowly. Whether that influence is biological, technological, or informational remains entirely speculative. There is no evidence that Atlas carries anything of the sort. Yet the speculation forces us to examine our assumptions. We often imagine contact as dramatic, a signal, a landing, a message, but contact could be ambient, diffuse, embedded within natural processes. If such strategies exist, they would exploit our tendency to dismiss what appears ordinary. And that brings us back to Atlas. An object behaving almost exactly as a comet should, shedding gas, following gravity, remaining silent, If the most effective strategy is patience, then drama would be counterproductive. The object would not need to change course. It would not need to broadcast. It would only need to continue being what it appears to be. And perhaps that is the quietest, most unsettling possibility of all. If you are still listening, still drifting through this silence with me, type 2 in the comments. When we speak about surveillance, seeding, or ghost technology, we are not really describing Atlas. We are describing ourselves reflected against the unknown. The dark forest hypothesis sharpens that reflection. In that framework, the galaxy is not a welcoming ocean but a shadowed woodland where every civilization moves cautiously, aware that visibility may invite destruction. In such a forest, silence is not emptiness. Silence is survival. If this is true, then the absence of signals from Atlas is not reassuring or alarming. It is expected. A civilization advanced enough to cross interstellar space would likely understand the risks of broadcasting its presence. It would study quietly. It would listen. It would avoid provoking unpredictable reactions. From that perspective, Atlas does not need to be artificial to make us uncomfortable. The silence mirrors our own uncertainty. For decades, humanity has transmitted radio waves into space. We have sent plaques, records, mathematical greetings. Yet recently, debate has grown over whether announcing ourselves is wise. Some argue that we should remain quiet, reducing our electromagnetic footprint. Others insist that contact is inevitable and hiding is pointless. The arrival of an interstellar object during this debate feels almost symbolic. Atlas becomes a test not of alien intent but of human psychology. Watch how we react. Watch how quickly curiosity becomes suspicion. Watch how rapidly reassurance turns into conspiracy. Cultural reaction is data. Every headline emphasizing speed, every thread speculating about hidden probes, every voice dismissing speculation entirely reveals something about our collective mindset. A calm civilization might respond with disciplined curiosity. A fearful one might default to threat narratives. A divided one might fracture into camps that cannot agree on basic interpretation. Atlas, by simply existing, has already triggered all three responses. The object has done nothing extraordinary beyond following gravity, yet it has activated deep cultural currents. That is the true mirror. The idea that we might be watched exposes our discomfort with vulnerability. The idea that we might be alone exposes our discomfort with isolation. Both fears exist simultaneously. We dread being observed by something more advanced. We dread being the only intelligence in a silent galaxy. Atlas forces both possibilities into the same frame. If it were artificial, then we are not alone, but perhaps not in control. If it is natural, then the galaxy may be filled with debris but not with voices, and the burden of consciousness rests solely on us. The great filter intensifies this mirror. If civilizations commonly destroy themselves before spreading widely, then the silence of space is not mysterious. It is tragic. Atlas, in that case, would be a fossil of ambition, a fragment of a system where life rose, perhaps even reached technology, and then vanished. The comet becomes an echo rather than a messenger. But if the filter lies ahead of us, then Atlas is not a fossil of others but a preview of our own potential fate. Our probes, our satellites, our machines may one day drift long after we are gone. Future astronomers on distant worlds might detect them and wonder about the species that built them. In that sense, every speculation about Atlas is autobiographical. We are projecting forward and backward at once. The dark forest suggests that civilizations remain hidden out of fear. The surveillance hypothesis suggests they observe quietly. The seeding scenario suggests they act slowly. The ghost technology concept suggests they outlive themselves. Each idea reveals what we consider plausible because of who we are. We know surveillance because we practice it. We know colonization because we have done it. We know extinction because our history is filled with collapsed cultures. Atlas becomes a canvas onto which we paint our experience. And perhaps that is its most profound role. Not as a probe, not as a threat, but as a psychological instrument. When an object older than Earth enters our system, it destabilizes our sense of centrality. We are reminded that our entire civilization occupies a thin layer of time. Beneath that layer stretches billions of years of cosmic history we did not witness. Beyond it may stretch billions more that will not include us. The arrival of Atlas compresses that perspective into a single point of light moving across the sky. It asks quietly, how do you respond to the unknown? With fear? With denial? With wonder? The media dilemma, the scientific caution, the speculative threads online all become part of the response. If an advanced intelligence were observing, it would not need to decode our languages. It would only need to watch our behavior. Do we cooperate globally to study the object? Do we share data transparently? Do we resist sensationalism? Or do we fracture into suspicion and narrative battles? Atlas may be nothing more than rock and ice, but it has already provided a dataset on humanity. It has shown how quickly imagination ignites. It has revealed how much trust we place in institutions and how quickly that trust can be questioned. It has exposed our longing for meaning in randomness. In this sense, the surveillance may not flow from the object to us. It may flow from us to ourselves. We are watching our own reactions unfold in real time. The object becomes less important than the mirror it holds. If the worst-case scenario is knowledge, then perhaps the knowledge is not about aliens at all. Perhaps it is about who we are when confronted with uncertainty. Atlas glides on its hyperbolic arc, indifferent to headlines, untouched by speculation. It does not accelerate beyond physics. It does not transmit. It does not deviate. It simply moves. Yet around that motion swirls a storm of interpretation. And that storm tells us more about humanity than any spectrograph could. If you are still listening, still reflecting in this quiet mirror, type 2 in the comments. There is a final layer to all of this, quieter than the rest. Strip away surveillance. Strip away ghost machines and chemical codes. Remove the dark forest and the silent seeds. What remains is something almost simpler and perhaps more unsettling. Atlas may be nothing more than ancient ice and dust, yet its presence forces humanity to confront scale in a way that statistics alone never could. It is one thing to read that the galaxy is billions of years old. It is another to watch a fragment of that age drift physically through your own solar system. Atlas becomes a mirror not because it hides intention, but because it exposes proportion. We are young. Our species has used radio for barely more than a century. Our telescopes capable of detecting interstellar objects have only recently matured. And yet we are already asking whether something might be watching us. That instinct reveals both ambition and insecurity. We assume that if intelligence exists elsewhere, it would be older, more advanced, more capable of subtlety than we are. Perhaps that assumption is correct. Perhaps it is projection. Atlas does not answer the question. It only sharpens it. Consider the idea of cosmic timing. If Atlas originated billions of years ago, then its journey began long before Earth formed oceans, long before life climbed onto land, long before mammals evolved, long before primates looked upward and wondered. For most of its existence, Atlas traveled through absolute darkness, passing stars that may no longer exist. Entire planetary systems could have formed and dissolved while it drifted. Civilizations, if they arose, could have flourished and collapsed in the time between its gravitational encounters. And now, at this precise sliver of time, it intersects with us. The coincidence feels theatrical, even if it is statistically inevitable. We happen to exist during the narrow window when our instruments are sharp enough to detect it. That convergence creates narrative tension, feels like arrival, but in cosmic terms, it is merely crossing paths. The human mind resists randomness. We seek intention. We search for signals hidden in noise. Atlas tempts that search because it sits at the boundary between the known and the vast unknown. It is only the third confirmed interstellar visitor. That rarity amplifies its psychological weight. If hundreds were already cataloged, Atlas would blend into background data. Instead, it carries symbolic gravity. The worst-case scenario, in its quietest form, may not be invasion or observation. It may be realization that the galaxy is older and more indifferent than we comfortably admit. Realization that interstellar objects may pass routinely unseen, and that our awareness of them is newborn. Realization that we are not central to these motions. Atlas did not adjust its course for us. It was not summoned by our radio waves. It is not responding to our technology. It was already moving long before we knew how to look. That perspective is humbling, and humility is uncomfortable. We prefer narratives where we matter directly, either as targets of observation or as unique survivors in a silent cosmos. But there is a third possibility, that we are simply another developing species in a galaxy filled mostly with natural processes unfolding over incomprehensible spans. In that case, Atlas is not a messenger or a warning. It is a reminder that physics governs everything from comets to civilizations, that time stretches far beyond our lifespan, that the unknown is not necessarily hostile, but it is vast. Yet even this natural interpretation does not dissolve the mirror. because how we respond to humility defines us. Do we retreat into fear, insisting that anomaly must equal threat? Do we inflate ourselves, assuming every rare object is a test designed specifically for us? Or do we expand quietly, accepting that mystery does not always carry intention? Atlas invites maturity. It asks whether we can hold uncertainty without filling it immediately with drama. It challenges whether we can remain curious without becoming paranoid. It pushes against our cultural reflex to polarize interpretation into extremes. In that sense, the object is already transformative, not because of what it is, but because of how we process it. If there are watchers somewhere in the galaxy, they would learn much from this episode. They would see a species capable of rapid global data sharing. They would see skepticism and imagination wrestling publicly. They would see fear tempered, at least in official channels, by mathematics and orbital precision. If there are no watchers, then the lesson remains internal. We are learning how to encounter the unknown without collapsing into myth. We are practicing, perhaps, for future discoveries that will be stranger than this. Atlas will depart. This hyperbolic path ensures it will not return. It will fade beyond the reach of our telescopes, becoming once again a silent wanderer between stars. But the imprint it leaves is not in gravity wells. It is in us, in how we think about surveillance, in how we debate the great filter, in how we imagine ghost technologies and silent forests. The comet may be entirely natural, yet the speculation it inspires is deeply human. And that may be the true story of Part 3. Not that Atlas hides machinery, not that it carries seeds, not that it encodes messages, but that it reveals our longing to understand our place in a universe where evidence is scarce and silence is vast. In the quiet space between data and imagination, we find ourselves reflected. Atlas is ice and carbon dioxide moving at extraordinary speed. But it is also a mirror held up against our fears, our hopes, and our intellectual maturity. If you are still listening at this point, still awake in the dark with these thoughts drifting gently through your mind, type 2 in the comments. The countdown now has a name and a date. October 29th, the day when 3I Atlas reaches perihelion, its closest point to the Sun, at a distance of about 1.4 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun. So at 1.4, 3I Atlas will still be farther from the Sun than Earth is. It will not cross our orbit. It will not threaten any planet. There is no collision hidden inside this geometry. Only illumination. Perihelion is not about danger. It is about exposure. For billions of years, 3I Atlas may have traveled through deep interstellar cold, warmed only faintly by distant stars. Now it approaches a region where sunlight becomes intense enough to awaken what has remained frozen. At 1.4 astronomical units, the Sun's energy is weaker than what Earth receives, but it is still powerful enough to transform ice into vapor. Surfaces crack. Frozen gases escape. Dust is lifted into space. What was silent begins to glow. Around the world, telescopes prepare in quiet coordination. Observatories in Chile, Hawaii, the Canary Islands, Australia, and beyond align their schedules so that as Earth rotates, one telescope hands the comet to the next. Space-based instruments adjust their windows to monitor specific molecular signatures. Scientists are especially watching carbon dioxide and water vapor, not as chemical formulas, but as simple frozen gases responding to heat. Carbon dioxide ice turns directly into gas at lower temperatures than water ice. That detail alone explains much of the early activity we have already seen from 3I Atlas while it was still far from the Sun. Perihelion will intensify that process. Heat is the most honest investigator in the solar system. It does not speculate. It does not imagine. It applies energy, and matter responds according to its structure. If 3I Atlas is simply an unusual comet from another star system, then October 29th will amplify its natural behavior. Carbon dioxide gas may increase dramatically. Water vapor, previously trapped beneath hardened outer layers, may begin to emerge. The balance between these gases could shift. The brightness curve will either follow predictions or surprise us. But surprise does not mean threat. The mathematics remain steady and calm. The orbit of 3I Atlas is hyperbolic. That means its eccentricity, the number that describes how stretched its path is greater than 1. When eccentricity is less than 1, an object is bound to the Sun and will eventually return. When it equals 1, the path is a borderline escape. But when it is greater than 1, the object carries more energy than the Sun can permanently capture. Imagine throwing a stone upward. If it travels slowly, gravity pulls it back. If you throw it fast enough to reach escape velocity, it never returns. 3I Atlas is already moving above the Sun's escape threshold. Even as gravity bends its path around the Sun, that bending is not capture. It is a graceful curve, not a trap. The path outward is already written in the equations. At 1.4 astronomical units, solar radiation increases compared to its earlier position, following a simple rule. The closer you move to the Sun, the stronger the energy, and that increase happens quickly. Energy grows as distance decreases squared. This means that small changes in distance can cause significant increases in heating. That heating will stress the surface layers of 3I Atlas. Carbon dioxide gas will escape more forcefully. Dust grains embedded in ice may be carried outward. Jets may strengthen. Scientists are not waiting for catastrophe. They are waiting for clarity. If the behavior matches thermodynamic models, confidence in natural explanations strengthens. If the gas ratios shift in unexpected ways, new questions will emerge, but still within the language of physics. There is no planetary defense activation, no emergency trajectory recalculation. The closest distance to the Sun remains well beyond Earth's orbit. Even in fragmentation scenarios, the scale of separation is enormous. The true significance of October 29th is not physical danger. It is informational gain. Perihelion is when hidden layers are revealed. When what was buried beneath radiation-hardened crust meets warmth for the first time in ages. When ancient ice, formed around another star, is forced to respond to our sun. And in that response, we learn. We learn whether carbon dioxide continues to dominate. We learn whether water vapor rises as deeper layers are exposed. We learn whether the brightness curve follows predicted sublimation models. Each observation either confirms our understanding or refines it. The worst-case scenario is not impact. It is misunderstanding, because illumination reveals more than composition. It reveals how we interpret uncertainty. As 3I Atlas approaches October 29th, anticipation builds quietly, not from fear, but from curiosity. The comet will not strike. It will not slow into orbit. This hyperbolic escape remains assured. It will swing around the sun, brighten under heat, release what it has carried for billions of years, and then continue outward into the dark. Sunlight will ask the question. 3I Atlas will answer in vapor and dust, and we will listen. As October 29th approaches, the focus shifts from distance to reaction. The question is no longer how fast 3I Atlas is moving, or from which ancient region of the galaxy it came. The question becomes simpler and more physical. What happens when sunlight presses harder against its surface? Heat is not dramatic. It does not explode or announce itself. It seeps inward, molecule by molecule, loosening bonds that have held for billions of years. Carbon dioxide ice, which transforms into gas at lower temperatures than water ice, has already shown us that this object responds earlier than most comets would. But perihelion will test the deeper layers. If water vapor begins to increase significantly, it suggests that beneath the outer crust lies a more familiar interior. If carbon dioxide continues to dominate even under stronger heating, then the internal composition may truly differ from anything formed in our own solar system. This is what heating tests chemically, tests layering, tests volatility, tests structure. Comet is not uniform. It is a history book frozen into strata. The outermost layers record billions of years of radiation exposure. Beneath that, older ice remains preserved, protected from cosmic rays. When sunlight penetrates, it drills gently through time. The gases that escape are not random. They are signatures of formation conditions. Carbon dioxide dominance suggests formation in colder, more distant regions of a stellar nursery. Water dominance suggests zones where temperatures allowed it to condense more easily. By measuring the ratio between carbon dioxide gas and water vapor as perihelion unfolds, astronomers are effectively mapping the birthplace of 3I Atlas without ever visiting it. But chemistry also provides another test, one less comfortable to speak about, yet important to frame calmly. Natural bodies behave irregularly, but within limits. Jets fluctuate. Brightness curves wobble slightly as rotation exposes new terrain. Dust production varies. However, all of these behaviors remain explainable by thermodynamics and rotation. If something were anomalous, it would not be a sudden dramatic maneuver. It would be subtle, a sustained acceleration not explainable by outgassing, a heat response inconsistent with known sublimation physics, a structural resilience beyond expectation. So far, nothing of that kind has appeared. The motion of 3I Atlas remains predictable. The tiny non-gravitational nudges caused by gas escaping from its surface fit neatly within cometary models. Its spin, inferred from brightness variations, suggests rotation rather than control. In short, its behavior continues to resemble nature. And yet, perihelion is where nature either confirms itself or surprises us. The sun becomes a laboratory furnace. At 1.4 astronomical units, surface temperatures rise enough to significantly increase sublimation rates. Pressure builds beneath crusted regions. When fractures open, jets can form, pushing material outward like gentle thrusters. But these are chaotic and asymmetric. They produce slight wobbles, not precision steering. If 3I Atlas were anything other than a natural comet, perihelion would be the hardest moment to maintain disguise. Materials engineered to survive interstellar space would still obey thermal expansion. Hidden cavities would vent. Internal structures would respond to stress. Heat is impartial. It does not cooperate with camouflage. That is why this moment is scientifically powerful. It removes the stability of deep cold and replaces it with dynamic change. The difference between natural and artificial is not cinematic. It is statistical. A natural comet's activity increases smoothly according to solar input. Gas production scales with temperature. Dust follows gas flow. Brightness correlates with sublimation. If observations across multiple wavelengths align with these expectations, then the natural hypothesis strengthens further. And if they do not, then new physical models must be constructed. Notice that none of this involves fear. There is no pathway from chemical anomaly to planetary danger. Even if fragmentation occurs, the distances involved remain immense. 1.4 astronomical units is over 200 million kilometers from the Sun and far from Earth. Debris disperses outward, not inward toward us. The gravitational geometry ensures separation. The only real transformation taking place is informational. Perihelion transforms uncertainty into measurement, compresses speculation into data. The sun shines, the comet reacts, and instruments record. In that simple sequence lies clarity. The hyperbolic path remains unchanged. Even as gas escapes and jets fire, the total energy of 3I Atlas relative to the sun stays above escape velocity. To alter that would require removing enormous kinetic energy, far beyond what sublimation can achieve. The mathematics are steady. The object will curve around the sun and continue outward. Heating does not rewrite gravity. So as October 29th nears, the anticipation is not about impact or intervention. It is about revelation. We are about to see the internal truth of a body formed around another star, tested by our sun's warmth. We are about to watch deep time respond to present light. Whether carbon dioxide continues to dominate or water vapor rises, whether jets intensify or remain moderate, each outcome refines our understanding. Perihelion is not a climax of danger. It is a turning point of knowledge. And knowledge, unlike fear, leaves us steadier than before. By the time 3I Atlas reaches perihelion, the distinction between natural behavior and imagined anomaly becomes clearer, not because mystery disappears, but because measurement tightens. There are specific signs astronomers look for when distinguishing ordinary cometary physics from anything that would truly challenge current understanding. A natural comet brightens in a way that follows predictable thermodynamic curves. As solar energy increases, sublimation increases. As sublimation increases, gas production increases. As gas production increases, dust is dragged outward, forming a thicker coma and sometimes a brighter tail. The relationship between these variables can be modeled mathematically. Temperature determines vapor pressure. Vapor pressure determines outflow rate. Outflow rate determines brightness and slight changes in motion. When plotted carefully, these relationships form smooth progressions rather than abrupt discontinuities. If 3I Atlas follows that pattern, then even its unusual chemistry remains firmly within natural boundaries. An anomalous behavior would not be theatrical. It would be precise and resistant to explanation. For example, if acceleration occurred in a direction not aligned with observed gas jets, that would be puzzling. If brightness increased without corresponding gas signatures, that would require new physics. If rotation suddenly stabilized in a way inconsistent with asymmetric outgassing, questions would sharpen. But nothing observed so far points in that direction. The small non-gravitational forces measured in its trajectory align with gas escaping unevenly from the surface. This is common in comets. Gas acts like tiny thrusters, but chaotic ones. They do not fire in synchronized patterns. They sputter. They fade. They respond to local topography and rotation. The motion of 3I Atlas reflects that messy reality. Mathematically, its escape is certain. A hyperbolic orbit means the total specific orbital energy is positive. In simple terms, the object possesses more kinetic energy than the sun's gravity can permanently remove. Even at closest approach, gravity only bends its path. The formula describing orbital energy depends on velocity squared minus gravitational potential energy. For capture to occur, velocity would have to drop below escape velocity at that distance. At 1.4 astronomical units, solar escape velocity is roughly 37 kilometers per second. 3I Atlas is traveling significantly faster than that relative to the sun. Outgassing cannot reduce that speed by tens of kilometers per second. The energy difference is enormous. Therefore, departure is not speculation. It is calculation. This mathematical certainty reframes the psychological tension surrounding perihelion. The worst-case scenario that popular imagination sometimes drifts toward: sudden capture, dramatic course change, hidden braking mechanism, does not survive contact with physics. For an object of this size to alter its trajectory meaningfully, it would require sustained thrust equivalent to advanced propulsion. No such thrust is observed. The brightness profile, the dust production, and the subtle orbital adjustments all match sublimation-driven activity. Gravity remains in control. The arc outward is as assured as the arc inward was. So if impact is impossible and capture is implausible, what remains? Interpretation remains. Perihelion forces a quiet confrontation with two broader possibilities that lie beyond immediate danger. The first is that we are being watched, not through beams of light or signals, but through presence alone. The arrival of interstellar objects in our era raises the question of whether they are merely debris or something more deliberate. Even if 3I Atlas behaves entirely naturally, the conceptual door has been opened. The galaxy can send travelers into our system. The mechanics allow it. The frequency suggests it is not rare. Therefore, the thought persists that somewhere, sometime, intention could ride similar paths. The second possibility is quieter and perhaps heavier. We may be alone. 3I Atlas may simply be an ancient fragment, shaped by gravity, chemistry, and time, carrying no message beyond physical history. If that is true, then the silence is not strategic. It is fundamental. The galaxy may be filled with debris but empty of voices. Each interstellar visitor then becomes a geological sample, not a diplomatic envoy. That interpretation carries its own weight. If we are alone, then the responsibility for awareness, for preservation of intelligence, rests entirely with us. Perihelion does not resolve this philosophical divide. It clarifies the physical story while leaving the existential one open. As heating peaks and begins to decline, gas production will eventually taper. The coma may thin. The brightness will crest and then slowly fade as 3I Atlas recedes from the sun. The hyperbolic curve carries it outward, past the orbit of Mars, past Jupiter, into regions where sunlight weakens again. The laboratory closes as the furnace cools. What changes, ultimately, is not the object's fate but our perspective. Before perihelion, speculation thrives in uncertainty. After perihelion, we possess refined data. The chemistry either confirms deep carbon dioxide dominance or reveals stronger water contributions from beneath. The activity either matches sublimation models or requires small adjustments to them. In either case, knowledge increases. Fear decreases. The mathematical certainty of escape, combined with the physical transparency of heating response, leaves little room for catastrophic narratives. Instead, it invites reflection. 3I Atlas came from beyond our solar system, endured unimaginable spans of time, briefly met our sun's warmth, and will continue outward forever. Whether it is a relic of alien geology or a silent witness from another epoch, its passage does not threaten us. It challenges us to think clearly. Perihelion is therefore not an alarm bell. It is a mirror. It tests ice and it tests imagination. And as the data settles, as the brightness peaks and gently falls, we are left not with panic, but with a calm acknowledgement of scale. The universe moves according to law. We observe, we calculate, we wonder, and then we let the traveler go. As 3I Atlas rounds the sun and begins its outward arc, the emotional temperature of the story cools even as the physical temperature briefly peaks. This is the moment when the phrase worst-case scenario quietly dissolves. There is no impact. There is no sudden maneuver. There is no hidden deceleration. The equations that described its arrival now describe its departure with equal precision. The same gravitational geometry that bent its path inward now guides it outward, symmetrical and indifferent. Hyperbolic departure is not drama. It is inevitability. The object entered the solar system with excess energy, and it will leave with excess energy. The sun cannot hold what never belonged to it. Yet psychologically, this turning point matters. For weeks, perhaps months, attention has been focused on what perihelion might reveal. Heating as interrogator, chemistry as testimony, motion as evidence. Now the answers begin to settle. The gas production curve reaches its peak and then stabilizes. Carbon dioxide output either maintains dominance or yields slightly to deeper water vapor layers. Dust emission aligns with rotation models. Each dataset closes a door that imagination once kept open. Not because imagination was foolish, but because it was incomplete. Data completes it. This is where we gently reframe the worst-case scenario. It was never collision. It was never destruction. The true tension lay between two existential interpretations. Either we are being watched or we are alone. Those possibilities still exist, but perihelion reduces their urgency. If 3I Atlas behaves like a comet under heat, if its jets remain chaotic and consistent with sublimation physics, if its motion continues to reflect natural forces, then the surveillance narrative loses weight. Not because surveillance is impossible in principle, but because this specific object offers no evidence for it. At the same time, the loneliness narrative does not automatically triumph. A single natural comet does not prove cosmic isolation. It simply demonstrates that debris travels between stars. It shows that planetary systems eject fragments into interstellar space. It reminds us that our own solar system has likely done the same countless times. Somewhere in the galaxy, pieces of our early history may be drifting silently, unobserved. So the two final possibilities remain but softened. If we are watched, it is not through overt spectacle. It would be through patience and subtlety beyond our current detection. And if we are alone, then 3I Atlas is a messenger not of intelligence, but of time. A relic older than Earth, crossing our skies without intention, yet still profound. Perihelion allows us to sit between these interpretations calmly. The object brightens and then dims. The coma expands and then thins. The tail curves gracefully, shaped by solar wind and radiation pressure. None of this signals intervention. It signals physics. And physics, though vast and sometimes strange, is deeply consistent. Mathematically, the certainty of escape continues to anchor the narrative. The total orbital energy remains positive. Velocity decreases slightly as gravity bends the path, then increases again as the object climbs out of the sun's gravitational well. This exchange is symmetrical. What was borrowed is returned. There is no hidden reservoir of thrust, no sustained force acting against gravitational expectation. Departure is not assumed. It is calculated. The psychological shift that follows is subtle but important. Anticipation gives way to observation. Observation gives way to understanding. Understanding gives way to perspective. The comet does not demand that we choose between fear and denial. It invites us to choose patience. It traveled for billions of years before we noticed it. It will travel for billions more after we forget it. Our role in its story is brief, and perhaps that is the calm resolution. 3i Atlas does not need to be a probe to be meaningful. It does not need to carry hidden messages to reshape our sense of scale. Its mere existence confirms that the galaxy is dynamic, interconnected, porous. Material does not stay confined to its birthplace. Stars exchange fragments indirectly through gravity's long reach. We are not sealed inside a cosmic bubble. We are part of a larger circulation. If we are watched, then our response to this visitor has already revealed something about us. We measured carefully. We calculated precisely. We resisted panic. We allowed speculation but returned to data. That behavior, if observed, would signal maturity. And if we are alone, then our calm curiosity becomes even more significant. It means intelligence, at least here, can meet the unknown without collapsing into fear. As 3i Atlas recedes from the sun, brightness fading slowly against the black, the sense of urgency fades with it. Telescopes will continue to track it for as long as possible. Spectra will be analyzed for years. Papers will refine models. But the dramatic phase passes. The comet becomes again what it was at discovery. A faint traveler on a clean, hyperbolic path. The worst-case scenario has not happened. No collision. No revelation of machinery. No cosmic alarm. Instead, what happened is quieter. We witnessed an ancient object respond to sunlight exactly as matter should. We tested our models against reality and found them resilient. We faced the tension between being watched and being alone and discovered that neither possibility requires panic. In the end, perihelion changes one thing most clearly. It replaces uncertainty with proportion. The sun shines, ice sublimates, gravity bends trajectories, the universe continues, and we, briefly illuminated by the passage of 3i Atlas, return to our own orbit around our star, a little steadier than before. As 3i Atlas continues its outward journey, shrinking slowly in brightness as distance grows, what remains is not spectacle but reflection. The perihelion moment has passed. The sun has done its work. Heat pressed against ancient ice, gases escaped, dust lifted, and the comet responded exactly as matter shaped by physics should respond. The hyperbolic arc now stretches outward, carrying it beyond the region of strongest sunlight, beyond the inner planets, beyond the easy reach of our most sensitive instruments. It will not circle back. It will not hesitate. The mathematics of escape are final. And yet, something subtle has changed. Not in the comet, but in us. We waited for illumination, and illumination came. Not in the form of hidden structures or impossible maneuvers, but in consistency. Carbon dioxide responded to heat in predictable ways. Water vapor, whether abundant or scarce beneath the surface, followed thermodynamic rules. Dust emission matched rotational exposure. Tiny non-gravitational adjustments in trajectory aligned with gas jets. The sun interrogated, and the answers were physical, not fantastical. If we are watched, then what was revealed is a species capable of restraint. We did not ignite panic over a distant object passing safely beyond our orbit. We calculated its velocity relative to solar escape speed. We measured its eccentricity, its specific orbital energy, its changing brightness curve. We allowed speculation to exist, but we anchored it to evidence. That response, if observed by any distant intelligence, would signal something important. It would show that curiosity can coexist with discipline, that imagination does not need to overpower mathematics. And if we are alone, then 3I Atlas becomes even more poignant. It is not a probe, not a message, not a test. It is simply a fragment from another star system, a relic of planetary formation processes that mirror our own. In that case, the meaning lies not in intention but in connection. Material formed around a distant star has brushed past our sun and returned to interstellar darkness. The galaxy is not silent because it hides. It may be silent because it is vast. Between these two possibilities, there is a quiet balance. Being watched does not require fear. Being alone does not require despair. The perihelion moment reframes both. The absence of anomaly is itself information. The certainty of escape is itself reassurance. The object's departure confirms that not every unknown conceals danger. Some unknowns simply pass through, offering perspective before fading. The psychological worst-case scenario was always about meaning, not mechanics. We feared what the object might represent, not what it might strike. But meaning, like orbit, stabilizes under careful observation. As data accumulated, the dramatic edges softened. The comet did not accelerate beyond explanation. It did not resist heat. It did not slow into capture. It followed gravity in and gravity out. There is calm in that symmetry. The sun pulled, the comet curved, and then climbed free. Velocity decreased approaching perihelion as gravitational potential converted kinetic energy, then increased again as it departed, restoring the balance. This exchange is the quiet poetry of orbital mechanics. Nothing was wasted. Nothing was concealed. The universe moved as it always has. As 3I Atlas recedes, telescopes will eventually lose it in the glare of distance. Its coma will thin. Its tail will vanish. It will become a point, then a whisper, then nothing visible at all. But its path will remain calculable long after its light fades. Years from now, models will still trace its trajectory as it crosses the outer solar system and re-enters the interstellar medium from which it came. What remains for us is perspective. We witnessed an object older than Earth respond to our star's warmth. We tested physics against an interstellar traveler and found no contradiction. We explored the possibility of being observed and the possibility of solitude, and neither demanded panic. Instead, both invited humility. The universe does not rush. 3I Atlas traveled for billions of years before we noticed it. Our observation lasted months. This journey will continue long after we are gone. In that scale, urgency dissolves. Fear shrinks. Even speculation becomes gentler. Perhaps that is the final resolution. The worst-case scenario is not already happening. What is happening is simpler and more profound. The galaxy is dynamic. Matter moves between stars. Gravity writes elegant curves. Heat reveals composition. Intelligence, at least here, can observe without collapsing into chaos. We are left with two open possibilities, but neither disturbs the calm night sky. Either somewhere intelligence watches quietly across unimaginable distances, or the silence is genuine and we are rare beyond measure. In both cases, our response matters more than the comet's nature. We measured carefully. We waited patiently. We let data speak. 3I Atlas has turned around the sun and is leaving. The furnace phase is over. The illumination phase has passed. The lesson remains. If you are still listening, still drifting with this ancient traveler as it fades back into the dark between stars, type 3 in the comments.